we've been talking about current, we've defined some material properties, and we've seen an electric field. But we haven't quite talked about yet is electric potential, or potential difference. So let's now try to bring that back in and see how that connects up. So let's think about a section of wire here. It's going to have circular cross-section just for simplicity. And we're going to say that a current is flowing. So if a current is flowing, there must be an electric field pointing in the same direction. And again, we're going to model that as a uniform electric field. But notice that if you have a uniform electric field, that means that you have a potential difference. And if we know the length over which that potential difference occurs, we can relate that exactly back to electric field. This starts to look like the relationship between the difference between two parallel plate, between a parallel plate capacitor, since we have a uniform electric field. So again, what I'm trying to go through now is relating back to electric potential, largely because it's something we can directly measure. Electric fields we see evidence of, but we typically don't measure them directly. A current we will be able to measure. We can actually see the evidence of it. So this is a way of now bringing in electric potential in place of electric field. And this is again going to move us back to circuits, because if you remember, we said that things like batteries actually cause differences in electric potential. So we know many things. That's a true statement in general, but let's think about our known quantities here. So our electric field is delta V over delta S, and this is true if you have a uniform electric field only, which is the case we have here. And so in our specific scenario, delta S, or the difference in this coordinate, is just going to be L. So our electric field is delta V over L. And again, we would say in our equation, E is appearing, so we're going to be plugging this in. So we're trying to bring in delta V, this difference in electric potential, to the equations where previously electric field has appeared. Current is then equal to current density times the cross-sectional area of our wire. And we said that current density, J, is just equal to sigma, the conductivity of our wire, times electric field, but we can go from conductivity to 1 over resistivity. So again, I'm just combining a bunch of equations together that have already appeared in the videos. So nothing new has happened yet, other than we're mixing some stuff together. So what we're next going to do is pull this in for electric field, which gives us L on the bottom and delta V in place of E. So we now have current is equal to some stuff times delta V. Why do we care about that? Well, notice that these terms here is the cross-sectional area of the wire, the resistivity of the wire, rho, which is a property of the material, like is it gold, is it aluminum, and L, which is the length of the wire. So once again, we've broken out something that is just a property of the wire. Not only the material in this case, but both the material and the geometry of it, right? So we have its cross-sectional area and its length. But then, other than that, we have a relationship between the potential difference and current. Now, I want to point out here that we have made a few assumptions, especially this one. So we are using a very simplified model of what's happening in our wire, and what we're going to find out is that this is true in many, many cases, but it's not always true. So be careful to note that our derivation here is not perfectly general, and we will be defining the regimes in which you can use this result, but I want to point out that there are going to be situations where you can't use it. So again, a simple wire like this, it works pretty well, and we're about to come to something pretty important. So for now, notice that we've been able to relate current to the potential difference across the wire just in terms of properties of the wire itself. The other thing that's important about this is that before we were talking about current in terms of microscopic properties, right? Number density and things like that. Now these are all macroscopic properties. So we now have a macroscopic model of current, and that is going to be really useful for being in lab, making actual measurements, and working in an experimental way, right? You can actually measure these two things with like a ruler, and resistivity is something known of a material. So these are all directly measurable in lab or identifiable. So there's a property that's going to be called resistance, which is just 1 over that special thing. So that's what we have defined here. So resistance is the property of an object. The units are going to be ohms, and the symbol we use for ohm is the capital Greek letter omega, which looks like a horseshoe. If you draw it as a horseshoe, I'll know what you mean, which is a volt per an amp. And before, I didn't point out the units of conductivity and resistivity. Ohms appear in it, and now you can kind of see why. So ohms and resistance is a nice place to start, and you can see then why this quantity appears in the unit of resistivity and conductivity. So there's a really important distinction to draw here. We have resistance and we have resistivity. Resistance is a property of an object. I have to hand you a specific piece of wire for you to tell me what the resistance of it is. But resistivity is a property of a material. So if I tell you I have a gold wire, you can tell me what its resistivity is, but you can't tell me what the resistance is without knowing the length or the cross-sectional area of the wire. So that's the distinction here. And notice that resistivity does appear in resistance. So whenever we're talking about individual objects, we must talk about resistance, but we might use resistivity to calculate it. So be careful, these terms are really similar, but have very important differences. To give you a sense, if we're talking about a good conductor, again, this would be an individual object, the resistance of it might be a couple of ohms. Maybe it will be much less. Maybe it will be 100 ohms, depending on the scenario, but typically good conductors have a few ohms of resistance. And something is even just called like contact, that if you just put two things in contact, it's hard to get them in perfect contact. And so some resistance comes out of that. A really good insulator is going to have resistance of, say, 10 megohms or more. More than that is really hard to measure with common tools. And so this capital M, remember, it means million, so 10 to the 6. And so if you're at, say, 10 to the 6 ohms or 10 to the 7 or higher, that's going to be a really good insulator. So for instance, when we talk about air, we would have to talk about the cross-sectional area or the length of air that we're talking about. And that's going to be an insulator, but it still does have resistance defined for it. Something that's like gold, it doesn't necessarily have zero resistance, but it has very, very small resistance. So hopefully this gives you a sense of what we're talking about. We will be talking about a class of object called resistors, which are usually somewhere in between.